morning, everyone. My name is Dr. Shane Johnson from the University of Michigan and Shanghai Jiao Tong University Joint Institute. Let's get started. The rectangular vector components of a vector A are its components divided into x, y, and z components. When you define a coordinate system, we usually use what's called a right-hand rule. So in the right-hand rule, you put your fingers in the direction of x and you curl them towards y, and that defines the z coordinate system, or so the z coordinate. So that's helpful for defining vectors in 3D space, because we only need to define x and y, and then z is dependent on those two. So the vector A, as you can see in this slide, is then ax, ay, and az. Now, you can also express it in terms of coefficients. So the I, j, and k are the unit vectors in the x, y, and z directions correspondingly. And so the ax, ay, az are the coefficients of those, the magnitude of the vector in that particular coordinate direction. Now, if you wanted to take the magnitude of A, we've already done that in the previous problem, but you take the square root of the sum of the squares. And so that's the magnitude of their Cartesian vector. If you wanted to define a unit vector, you would then take A in its components and you divide by the magnitude of A. And that gives you the unit vector for the A vector, right? So it's one unit in magnitude, but it's in the direction, in the same direction of A. If you wanted to define force resultants, of course, we can just, like we did in the previous problem, we can just add the different force vectors up. So we can say the sum of the forces in the x, the sum of the forces in the y, the sum of the forces in the z, in the I, j, and k coordinates, respectively. Vectors can be defined in 3D space, and as you can see it in this one, one of the ways that we define the components of a force is that we find the projections onto a plane. The 100-pound force in this particular image here, you can find its projection onto the xy plane first, and then you define those components. Then you could define the components that are in x, in y, and then, for example, in the z component. So we use the projections to be able to define the magnitudes in the different coordinate directions. And so you can see here the projection is taken. The 100-pound force becomes the F becomes F prime as the projection, and then you, with a 45-degree angle on that projection, you can define the Fx and Fy, and then of course the Fz in the vertical axis. And the angles can then be defined from each of the axes, and these are typically the alpha, beta, gamma angles. So this one shows the alpha, beta, gamma angles for the force F that would define the system. So in this one, we can determine the x, y, and z components of the force F, and the angles beta and gamma and the magnitude of F are given to you. F is defined by the components alpha, beta, and gamma. And so we can define a unit vector U F is equal to Fx over the magnitude of F in the I direction plus Fy over the magnitude of F in the j direction plus Fz over the magnitude of F and in the k direction. Okay, now another way that we can define the unit vector would be that we would say UF is equal to cosine of alpha in the I direction plus cosine of beta in the j direction plus cosine of gamma in decay direction. This is a convenient form because if we want to know, we know that the magnitude of a unit vector is 1, so we can go ahead and we know the relationship then between the alpha, the beta, and the gamma would be something like this. So you'd say the magnitude of the unit vector here is equal to 1, is also equal to the square root of cosine squared alpha plus cosine squared beta plus cosine squared gamma. So we can just say then, well, okay, well then that's equal to 1 is then equal to cosine squared gamma plus cosine squared beta plus cosine squared gamma. Okay, so this is nice because we know what beta is and we know what gamma is. So then cosine alpha is equal to the square root of 1 minus cosine squared beta minus cosine squared gamma. It's a quite convenient form. And so you can then define alpha is equal to cosine inverse of the square root of 1 minus cosine squared beta minus cosine squared gamma. Okay, so that gives you the angle, and then you can just do the force F in the rectangular coordinates, or the actually Cartesian coordinate system here is what happened there? Okay, 400 newtons times cosine of alpha I plus 400 newtons times cosine of beta j plus 400 newtons times cosine of gamma k. All right, so I would let you, with your calculator, go ahead and plug in what the cosine of these terms are, since now you can easily solve for the alpha and beta and gamma are already given. So this is how you would set up a problem like this one, and you can define what the components of f are. It's quite instructive to work on problems that we define a vector by coordinates. This is common in problems that have cables or rods where the force is along the length of the member. For example, the cable AB. We can define the cable AB as that it starts or originates at A and terminates at B. That can be a force that goes from A to B, and then to define it we need to define the coordinates of A and the coordinates of B, and then we can start to define that force vector knowing the magnitude of that force. Now in this problem it's just an instructive problem to get us to get started. So in this one, we want to determine the z-coordinate of B. So let's start to just define what are the coordinates of A and B, and then to define a vector from A to B. The coordinates of B are, we have 0 meters in the x direction, and we have, let's see, 6 meters in the y direction, and we have, well, in the z direction we have z. And the coordinates of A then are 3 meters in the x direction, 0 meters in the y direction, and 2 meters in the z direction. Now when we define a vector that is going from A to B, we can call that, let's call that RAB, and this is a vector now, is equal to, and we'll just make a subtraction between these three terms to define the ij and k components. So we have 0 minus 3 meters in the I direction, plus 6 meters minus 0 in the j direction, plus z minus 2 meters in the k direction. So this is the RAB vector with ijk components. Now you can see in this problem we have a z here, so we have one unknown. But if we determine the magnitude of RAB, then that is given as 7.5 meters. So if we determine the magnitude, then we should be able to solve for z since we have an additional known in the problem. So let's do that. Let's take the magnitude of RAB. So here's RAB magnitude is equal to square root of minus 3 meters squared plus 6 meters squared plus z minus 2 meters squared. All right, and so all of this we know is equal to 7.5 meters. So now we can square both sides of this equation and then try to get this this z on one side of the equation. Square both sides of the equation to get out the radical. So let's do 7.5 meters squared. And then we'd have everything under here, so we can subtract 9 meters squared minus 36 meters squared is equal to z minus 2 meters squared. Okay, now we can take the square root of both sides here, and then we have the square root of 7.5 meters squared minus 9 meters squared minus 36 meters squared, and then we're going to have to add 2, and then this is equal to z. Okay, and I'll let you solve for the z, and this is how you would go about defining a vector. So this is the RAB vector, and then how to solve for an unknown like a coordinate if that's something that you wanted to do. All right, we're going to do now one more problem with this with force vectors on a basic level to combine the forces FB and FC in this one. So what we're going to do is we're going to solve for the force resultant of FB and FC. So to do that, we're going to have to find a few things. So you can see what's given now in the problem is we have the magnitude of FB. What we don't have, so we have the magnitude of FB here. We don't know what the components of this are to be able to add the two together. So we have a few choices, which we can do some just basic geometry here and have the projections. Many times, as I've seen in exams, when people try to do this, they have a higher risk of having a mistake in the problem as they solve it. And you can see FC here, we have the magnitude of FC, and it makes it easiest for us to break it into projections. But instead what we're going to do is we're going to break this problem into Cartesian coordinate systems, and then we're going to add those components together to see what the resultant force is on the hook at A. You can see here, right? So, so what we're going to do now is we're going to find the vector that goes from A to B to start out. So, so to do that, let's have first the coordinates of B. So we have the coordinates of B are, so first in the x, 3 feet in the x, and in the y we have, so this is the positive y-axis over here. So if you use the right-hand rule, you would have from x to y, you put your fingers in the direction of x, curl towards y, and the z would be defined by your thumb. So that means we have negative 3 feet in the y direction, and in the z direction it's defined here 2.5 feet in the z-axis. So 2.5 feet in the z-axis. Then we have to find the coordinates of A to be able to find the vector RAB. But so we'll define that in a second. So the coordinates of A now are, so you can see 0 in the x, 0 in the y, and 4 feet in the z. So 0 feet, 0 feet, and 4 feet in the z. All right. So now we can define a to define a vector RAB by the subtraction of these two. So that's 3 feet in the I direction, and -3 minus 0, so -3 feet in the J direction. And then we have 2.5 feet minus 4 feet. So that will be minus, where are we here? So that would be minus 1.5 feet in the K axis. So now this is the direction vector that we're looking for. Now it has a magnitude for itself, so the first thing that we'd have to do is we have to find the unit vector UAB that's in the same direction as the FB, the force that we're looking for here. So so the next thing is we want to take the magnitude of RAB is equal to the square root of 3 feet squared plus -3 feet squared plus -1.5 feet squared. So then just a second. So that is equal to so that's going to be equal to 4.5 feet for the magnitude of this RAB. So that's helpful because now we can we know what the unit vector is. We just have to divide the RAB by the magnitude of RAB. And then we can add all of that together later. So let's find the vector, the components of the vector FC. So we can do that easily by first finding the components of C. And so that would be for the x direction 2 feet, and then for the y direction 4 feet, and then for the z direction 0 feet. Now again, for the components of A, we have that up here. So we'll subtract C, I'll have C minus A. So for the direction vector RAC, this will be the components of C minus the components of A. So that would be 2 feet in the I, plus 4 feet in the J, and then we have 0 minus 4 feet. So minus 4 feet in the K direction. Now we want to find the magnitude of RAC. the square root here. Looks like I'm missing a t here for feet. Okay, so for this we'd have 4 feet squared plus 16 feet squared plus 16 feet squared. So that's 36 feet squared. So the magnitude will be just RAC is equal to 6 feet. So now we could begin to add those components. So I'm just going to now size down this diagram so I have a bit more space here, and then I can work a bit here. So now what we would want to do is we want to add the x and y and z components of the force vectors FB and FC so that we have the resultant. So what we're going to do first is we'll take the FB is equal to 600 pounds times. Now we have to have the unit vector of FB. So that's 3 feet in the I, and we're going to divide by, and this could be even easier if we just divide out here by the 4.5 feet here on the outside. So 3.5 I minus 3 feet J minus 1.5 feet in the K. And then we have FC, which is equal to 750 pounds. We'll divide here by 6 feet. And then you have the RAC, 2 feet in the I, plus 4 feet in the J, minus 4 feet in the K, right? And so all we're going to do is we're going to add these two vectors together. So this will be now just multiplying some of these things out. We have FB, and I should have vector notation on top of all of these. And so what we'll do is we have FB is then equal to 400 pounds in the I minus, minus 400 pounds in the J, and then we have minus 200 pounds in the K. FC is equal to 250 pounds in the I plus 500 pounds in the J minus 500 pounds in the K. Now we have the force resultant FR is going to be the summation of these. Well, that's now then very easy. 650 pounds in the I direction, 100 pounds in the J direction. Make sure everybody sees that's positive. And then minus 700 pounds in the K direction. Just adding up the components of the IJK for the FB and FC. So that's the resultant. Now, after you did this, what you'd want to do is you want to look back and you see, does that make sense? If I added up those two vectors, so visually with this drawing, does that make sense, or have I made a big mistake? This is just a visual way of looking at it. So what we do is we say, look at the FB and FC are in, one of them is in the negative y, one of them's in the positive y. So we know that we would have to add those together. The force resultant would be somewhat closer to the x-axis. So you can see here, this was a negative 400 in the J for the FB, a positive 500 pounds in for FC. So then we have to sort of get a lot closer to the x-axis, or closer to 0, with this force resultant here. So that, to me, that makes a lot of sense, right? How about the for these other components? Both FB and FC are pointed to the negative z. So you can see them pointed towards the negative z here. So that means you should be adding two negatives here. So you got negative 200 and negative 500. You have something that's even larger for the force resultant in the z-axis. And the same kind of understanding you're going to do for the x-axis as well. So force vectors. So in this lesson, you learn how to combine vectors in 2D and in 3D. You learn how to work with the units in those, how to calculate a unit vector, how to calculate a magnitude of a vector, how to use those to find some unknown quantities, how to find the force resultants in many different systems. So this is the basics. I hope that you practice the problems, and there will be some homework assigned such that you can try these problems out. In addition to using Cartesian coordinates to find force resultants, you also use the parallelogram rule, the triangle rule. You use law of sines and law of cosines, and these are really helpful for solving a lot of problems. So you have to both visualize the problems, which is really helpful from the triangular and the parallelogram rule. You also learn how to calculate them, and maybe it's easier to make less mistakes if you use just additions in Cartesian coordinate systems. So I hope that you can both visualize and better calculate with less risk in the problems that you solve. So as you see that we solved several problems here, and hope that you could follow along and enjoy some of those, how to work out some of those problems. So go back, study in the homeworks, come back to the video, try to go through and see how some of these problems are worked out. We also have in class, you'll have some time for some questions. So prepare your questions, and let's get ready for Chapter 3 coming up. Thank you.